Good morning. Thank you for having me here to speak. I'm sorry I don't speak Bulgarian. If you find that my English is too fast or too colloquial, please feel free to stop and ask me what I'm saying. But I've lived about 10 years in the non-English speaking world, so my English is a little bit adapted these days, so I think I'm not too uncomfortable for non-native speakers. But maybe I'm wrong. My name is Michael Kerrisk. What I do, professionally, I'm a programmer. I've also been a writer, a teacher as well. I've been working with Unix and Linux for about 25 years. Obviously not 25 years with Linux, but nearly 25 years now with Unix. I've been involved with Linux in a serious way for about 10 years. I first started playing with it a bit further back than that, but 10 years has been when I've started contributing, if you like, to Linux. In 2004, I became the maintainer of the man pages project. The man pages project is the man pages that provide the documentation for the kernel and glibc programming APIs. There's about 950 pages in the project. The project's been going for actually close to 20 years. And I've written about 250 or co-written about 250 of those pages. Along the way, I've done lots of testing of interfaces. I found quite a lot of bugs. I think, okay, and I happen to have written a book. Marian nicely spoke about it. And I've spent an awful lot of time looking at the Linux programming interface. So my talk, the title, Why Kernel Space Sucks, the title draws on a very amusing talk that a guy called Dave Jones gave in Ottawa in 2006. Dave Jones, some of you probably know his name. He's a very well-known kernel hacker. And he gave a very amusing talk standing up, presenting various ways in which user space applications mess things up. I certainly can't argue with anything that Dave says. Probably 100% of it was right. But on the other hand, I want to point out that sucking goes in both directions. And there are ways in which kernel space sucks for user space. And I'm going to talk about just one of them, which is the one that is of interest to me, which is the interface between the two. Those are the URLs for Dave's talk in case you want to go back there and have a look. And Linux Weekly News did a very nice short summary of the talk as well. I'll abbreviate the talk in my slides as WUSS, which is an amusing abbreviation as I'll come back to later on. So Dave Jones' motivation was he's a kernel hacker. Kernel hackers are interested in making the kernel go as fast as possible, do everything as efficiently as possible. And he turns on his machine each day and he finds, well, it's really slow. It takes a long time to boot up. It even takes a long time to shut down. And why do applications take so long to start? And so, oh, and one more thing, of course, why does the battery life go so quickly on his laptop? So he started instrumenting his kernel to get some picture of what was going on. So, and he created essentially a log of the various system calls that took place as a system started, well, during the whole lifetime of the system, but he was particularly interested in when on startup of the system, boot, and obviously the startup of applications. And these are the sorts of things he found. During boot, 80,000 files were statted. Now, if you are not familiar with the low-level interface on Linux, stat is the system call that says, tell me the attributes of a file. So 80,000 files were inquired about. Tell me about this file. What are its permissions? How big is it? And so on. 27,000 files were opened. 1,400 programs were started. And on shutdown even, 23,000 files were statted and 9,000 files were opened. These are quite extraordinary numbers. So what his conclusion was is that user space programmers are wrecking performance doing crazy things. So things like opening and reparsing the same file multiple times. So one of the things he found, for instance, was that HAL, which was the abstract hardware abstraction layer used back in the day, but pretty much obsolete now, was opening XML files multiple times, parsing them up to 54 times for the same file. No caching, just read the file, parse it again, forget about it, read the file, parse it again, forget about it, and so on. Other applications read device config files for devices that weren't even present on the system, and they did it for hundreds of devices. Or they statted hundreds of files, for example, font files, that they would never need because they were never going to display any text. Or they kicked off timers that work up the system to do nothing. So a good consumer of battery power on your laptop. So Dave's conclusions were there's obviously room for a lot of improvement in user space, and there should be, every user space developer should be aware of trace tools and analysis tools, things like LTT and ftrace, system tap, and so on. Things that actually evolved quite a lot since the time that Dave gave this talk. There's a lot more of these tracing tools nowadays and are better. And probably the user space is better now, but there's probably still room for lots of improvement. Now, if you have a famous kernel hacker standing up and giving a talk called Why User Space Sucks, you might get the impression that the world looks like this. The kernel is paved with gold, and user space is a bunch of old lead. And if you were comfortable enough in English, you might wonder if it was a coincidence that WUSS, wuss, is a person regarded as timid or ineffectual. And you might draw this overall implication. We kernel developers are much smarter than user space programmers. I want to be a little fair to Dave. I don't think that's what Dave was trying to say, but if you came to his talk or read it after the fact, you might draw that conclusion. Dave actually did point out one or two places in his talk where kernel space also sucks from a performance point of view. But you might draw that conclusion. For me, there's something wrong with this picture. And I want to use Dave's talk as a jumping off point to question a couple of myths, or what I consider to be a couple of myths. One of them is kernel programmers, these really smart guys, can always get things right in the end. And the other is that code is the best way to contribute to a software project. So let's start with the first one. Kernel programmers can always get things right in the end. We're talking about the crown jewels. Okay, we're talking about Linux. We're talking about the crown jewels of open source, if you like. We're talking about some really smart programmers. Surely they do get it right. If not at the beginning, then through some iterative process, they get it right by the end. In truth, they don't. There's at least one place where they don't. This is the place that interests me. It's the interface between kernel space and user space. And I want to deconstruct this myth of perfection or excellence. So when I talk about the interface, this is what I'm meaning. The various pieces that the kernel presents to user space, system calls, pseudo file systems like /proc, /sys, IOCTL interfaces. Okay, IOCTL is, of course, a system call. but it's the interface to device drivers, and often IOCTL is used to present this little universe of a device driver to the outside world. So IOCTL can often present quite a grand interface for a device. So I've separated it out into its own category. Netlink sockets and some obscure pieces like the auxiliary vector and the virtual dynamic shared object. I'm going to concentrate mainly on system calls. The other piece we encounter most often, they're the biggest piece, more or less, of the interface. So what I want to start with is an observation. API designs have to be done right the first time. Obviously, perfection is not possible, but we need to do it as well as we can. And why is that so? Well, when you're talking about code, you get a picture like this. If you rated the kind of problems that you're trying to solve from trivial through to easy to moderately difficult through to difficult to impossible, code problems tend to fall all along that boundary. They tend to be trivial one-liners that were obvious, through to problems that are difficult, occasionally problems that are impossible, okay, something that's algorithmically impossible, but most code problems fall in the band from trivial through to difficult. But API changes tend to fall like this. If you want to change an API, it's either difficult or it's impossible. And the reason is that changing an API, fixing an API, means usually breaking it for some user space applications that already depend upon it. And this is what Linus says: we care about user space interfaces to an insane degree. We go to extreme lengths to maintain even badly designed or unintentional interfaces. Breaking user space programs isn't acceptable. Or, as I heard him say more recently, I'm very unhappy when we break user space. So, when it comes to APIs, Marian is trying to indicate something to me. I'm not sure what. Maybe Marian... Okay, Marian has my books. If someone wants to buy a copy of my book. When it comes to APIs, there is no getting things right in the end, because usually there isn't room for iteration. If you don't get it right first time, you don't get many chances to clean up. So you have to be as smart as possible first time round. What that means is that any time a kernel developer makes a mistake in design of the API, that creates pain that thousands of user space programmers have to live with for decades. What do I mean by getting an API right? Okay, whoops, there's a little font size problem there, my apologies. I don't need to go into too much detail on all of these, but very roughly, these are some things that I think an API should get right in order to be considered good. You know, obviously, it should be bug-free. Yeah, seems obvious, doesn't it? It should have a nicely thought-out design, simple as possible, easy to use, difficult to misuse, should be consistent with related interfaces. It should integrate well with existing interfaces. How does it interact with fork or exec or threads or signals? It should be as general as possible, not just a single use case for it, but designed to fit multiple use cases. It should be extensible in case we do decide that we want to do more with the interface in the future. There should be ideally some path to extend that interface, and I'll come back to that later on to explain what I mean. It should adhere to standards. The very last point that I have there, it should be as good or better as similar APIs that it is replacing. Again, that seems obvious, but in fact it is not always true. How do the developers Score, the kernel developers. Any BSDers in the room? None? You laugh quietly, please. And be happy that I'm not looking at your interfaces. Okay, bugs. We really shouldn't have bugs in freshly released APIs, should we? Well, it turns out that if I look at the history of system calls that I've looked at that have been released over the last few years, probably 50% of them, that's just a guess, have some significant bug at the time of release. Okay? So utime NSAT, which is a system call for setting file timestamps, when that was released, it had about 4 or 5 different non-conformances to specification in POSIX. Released in 2.6.22, fixed only 4 releases later when I happened to write the manual page about it and complained, or wrote some tests. Signal FD is a technique for receiving signals via a file descriptor. It didn't correctly actually send data or receive data that was sent via the SIGQ system call, which is the way of sending a signal with an accompanying integer that has supporting data for the signal. Fixed 3 releases later. Just a few other examples. A few URLs there that'll point you to more information about those. Okay, iNotify didn't work at first release with one of its flags. Splice had a quite spectacular bug from my point of view. It was really easy to write an application that would just freeze. You could create an unkillable process. TimerFD, again, a significant bug on initial release. I'll come back and I'll talk about TimerFD in another way later on. So, not looking so good with bugs. What's going on? There are just way too many bugs from my point of view in released interfaces. There's obviously not enough pre-release testing. There's too few testers. Often it's the kernel developer only. Sometimes I'm afraid it's not even the kernel developer. Certainly looks that way sometimes when I've seen some interfaces that have come out. Obviously there's no unit tests. There's not a lot of test coverage sometimes. And often there's no clear specification against which to test. In other words, there's no written document that says this is how the interface is supposed to work. So that you can write a test to see, does it actually work that way? Even when the bugs are fixed, user space may still need to care. What I mean is, if you're writing an application that depends on a particular interface and it had a bug that got fixed, well, your application may still need to know about the buggy kernels. You may need to special case your application to deal with the old buggy kernels. Designs, I think there's a good argument that we don't tend to think enough about our designs for interfaces that are shipped from the kernel. So here's a simple example. There's 3 system calls there. Each of them nowadays has an argument that it doesn't use. It serves no purpose whatsoever. So for instance, ePollCreate had an argument, a size argument that specified the size of an internal, or the expected size for an internal kernel data structure. I don't think that argument should ever have been there. Why should user space have to try and specify some information that gives the kernel some estimate of how big its internal data structure should be? That's a decision the kernel should make on its own. And user space shouldn't have to worry about it. So all 3 of those interfaces, there should never have been these arguments there in the first place. And eventually someone worked that out and made these interfaces, made these arguments do nothing. Further examples in this line of, let's code it now and let's think about it later. FU times AT, it's an extension of U times, which sets file timestamps. It was, if you like, the predecessor of a system call that I talked about a moment ago called utimes NSAT. It was proposed for inclusion in POSIX 2008. Before that standard came out, it was implemented on Linux. The POSIX committee turned around and realized this interface simply isn't sufficient. There were some obvious use cases that the system call or the proposed system call couldn't do. And so they standardized a different interface. And that was utime NSAT. So we've got a crummy old system call there, futime 80. No one ever wants to use it. But we can't get rid of it because there might be someone out there that's using it. Okay? And that's the history, or that's the problem with kernel interfaces. You can never get rid of them because, well, almost never. Because someone out there might have some old application that still is using them. And you've got no way of finding who those people are and telling them how to fix it. The world's too distributed for that. Similar thing, there's a very nice system call on Linux called PollWait. It's an improvement on the traditional select system call, which allows you to wait for multiple file descriptors. It was added in Linux 2.6. In Linux 2.6.19, we added PollWait, which is just the same system call, but it also allows you to manipulate the signal mask during the call. Because it turns out that some applications that want to wait on file descriptors also want to temporarily block or unblock signals while they do so. PollWait does everything that PollWait does. We don't need PollWait anymore. We could have just had PollWait at the start. And the question is, well, why didn't we think about that? Because already in 2001, the POSIX committee had suggested that, or had standardized exactly the same analogous interface for select called pselect, solving exactly the same problem. In other words, the problem was already well known, the solution was already well known. We turned around and implemented an insufficient interface at the start and then had to go and fix it. And we created some cruft along the way. Consistency. We want to have consistency in our interfaces, right? Well, it makes life easier when things are consistent. So here's an example of a wonderful inconsistency in the kernel user space interface. There's a lot of system calls that have an interface something like this. That they work on memory address ranges. You specify a start address and you specify a length. And a lot of those system calls, for example, mlock, behave like this. They round start down to the page size, so you don't have to round it yourself. I'll just round it down for you. And they round length up to the next page boundary. So if you say mlock 4,000, 6,000, assuming a 4 kilobyte page size, that'll affect the bytes in the range 0 to 12,287. Then you get a system call like this, which is a Linux-specific system call added in 2.6. Round start down to a page boundary. That looks familiar. Round length down to a page boundary. If you do a remap file pages 4,000, 6,000, what address range is affected? Assuming a 4K page size. It's not none, but it's 0 to 4K. I regard that as a disaster. It was a disaster actually implemented by one of the most famous kernel hackers. So even the smartest people are making these sorts of mistakes in designing kernel user space interfaces. The problem, of course, is that users expect that interfaces that look similar will behave similarly. So if I was used to using mlock to lock memory, and I wanted to work with the address range 4,000, 6,000, starting at 4,000 up to 6,000 bytes after that, I might then turn around and use remap pages in exactly the same way. And I'd make a false assumption, and I would create a bug. It might even be a quite hard to find bug, or it might be an easy to find bug. Further in this same line, there's a bunch of system calls that allow one process to affect the attributes of another process. And so I've just listed a few examples there. Normally, if you're talking about an unprivileged process, then the system calls require some sort of credential matching between the two processes. So the UIDs of the caller, or some of the UIDs of the caller, must match some of the UIDs of the target process, or perhaps it's based on group IDs, and so on. But there's some combination of caller credentials that must match the target's credentials. The problem is that there's an awful lot of inconsistency again. So these are 4 system calls there and the rules that specify the credential matches that are required. I don't want to go through those all in detail. I just wanted to point out that there is inconsistency. If I can make this laser pointer go, if I can remember how to make the laser pointer go. So, for example here, set priority, the effective user ID of the caller needs to equal the target's real user ID. This is what my notation here means. Or the effective user ID of the caller needs to match the effective UID of the target. And so on and so on and so on. The point is not what each system call does, but they're all different. Now, what that means, again, is you've got this inconsistency, and it's an inconsistency that impacts in a different way. If you've got a program, a privileged program that wants to make use perhaps of 2 of these system calls, it may be that you need to mess around with the user IDs of your process to switch them around in order to make one system call, and then switch them again in order to make the other system call. Now, anytime you do that, there's the possibility for a mistake. And it's a mistake with credentials. And if it's a mistake with credentials, it's a security bug. So this inconsistency helps people create security bugs. Any questions so far? Okay, interfaces should be designed to be general. So back in 2.6.22, Linux added a nice interface called TimerFD. The nice thing about TimerFD is you can create a timer that delivers its expirations via a file descriptor. Because this is a classic problem in Unix systems. You've got an application that's using select to wait on multiple file descriptors, and it also happens to be using timers. And the question is, how do you wait on file descriptors and on timers? You used to have to go through some hoops to both catch the timers via signal handlers and wait for the file descriptors with select. TimerFD creates a nice solution to the problem. You can have a timer that generates data on a file descriptor when a timer expires. It's a nice idea. This is how the interface looked at the very beginning. You specified, this was either -1 if you were creating a new file descriptor, a new TimerFD file descriptor, or it was the idea of an existing a TimerFD file descriptor, some flags for the call, and a specification of the timer's interval and start time. The problem is that the interface didn't allow you to do things like changing a timer, an existing timer, and retrieving its previous value at the same time. And it didn't allow you to do things like saying, I want to know how much time is left before this timer expires. The only thing you got was information that when the timer expired. The thing is, there were already some existing timer interfaces on Linux or on Unix systems that did this. getItimer, setItimer, and POSIX timers, the timer underscore system calls, if you're familiar with them. they gave you exactly that functionality. Now, what this meant is, for timer FD, with an interface like that, it probably would impact how you would write libraries. You couldn't, for instance, write a library that might modify the program's timer FD timer temporarily and then reset it back again later, because there was no way of saying, set this timer, adjust this timer, and get its previous value so that I can restore it later. So the solution to the problem was that the timer FD system call was disabled in 2.6.23. And then eventually in 2.6.25, we got it right. Timer FD create, timer FD set time, timer FD set time. This is exactly analogous to the POSIX timers interface. If you want to be strict about it, that was an ABI breakage, because there was a different system call out there for one kernel release that we took away. But it was only ever in a single kernel version. It never made it into glibc. It's probably a reasonable bet that no user space application ever used it. So I said at the beginning, we should never break user space APIs. It's a continuum. Sometimes there's a trade-off. This was a reasonably safe trade-off, but you get less and less safe in changing user APIs, depending on how long they've been around, how many users they might have had. Okay, this one people decided they could get away with. Do we learn from the past? Are the things we create new better than the things that came before? Well, back in Linux 2.4, there was a thing called denotify. It allowed you to monitor changes in directories. It was for things like file management utilities, graphical file management utilities, so you could watch a directory and see what had changed in that directory and perhaps update the display for the user. It did that job sort of well, not so very well. One of the developers of iNotify used to joke that the D in denotify stands for suck. That was a bit cruel, but there were a lot of problems with the interface. So then we added iNotify in 2.6.13, but we still didn't get it quite right. It does things, it's a lot better, but it doesn't do some things that we now realize we'd like to do, like it doesn't tell us which process actually made the file change, which UID made the file change, and there's a few other pieces that it would be nice to have that it doesn't do for us. Okay, we already knew these problems were, we know by now these problems are there. We didn't perhaps realize them before. Okay, but by the time we came to implement yet another API in 2.6.37 called FA Notify, which did a similar sort of task, but it was oriented around people who wanted to write virus scanners. It added some of the missing functionality, but it didn't provide all of the functionality of iNotify. In other words, we've got now two file notification interfaces that are like this. They overlap, but they don't, one of them isn't the superset of another, which is what we should have had. Why didn't we do that? I think it's a question of people focusing too much on their use cases and arguing the point until they win. Interfaces should be designed to be extensible. What I mean for this is too often we've had an API, we realized after the fact it wasn't sufficient. The solution has commonly been to do something like this, create a new API with a flags argument that allows you to modify the behavior of the system call. So, for example, we had umount, which was a very early system call, obviously, for unmounting file systems. Eventually, we got umount2 in Linux 2.2. But we've kept making the same sort of mistake. epoll create in 2.6, epoll create 2 in 2.6.27, fu times at in 2.6.16. In .22, we had epoll. Oops, that's u times n is at. Okay, in 2.6.22. Signal FD in 2.6.22, and then signal FD4 in 2.7. We keep making this mistake over and over. So whenever we're adding new interfaces by now, we should always be thinking, even though the interface doesn't seem like it should need to be extended now, is there some way it might need it in the future? And should we just add an unused flags argument to the system call? If you do that, then you should always do this sort of check in the implementation, where the system call should have a check like this. If flags is something other than the flags we know about, give an error to the user. If the interface doesn't do that, I call it a loose interface. What I mean by that is, suppose you've got the system call and a user makes a system call, makes a call like this: syscall XYZ with the argument -1 for flags, -1 of course just meaning all bits turned on. Well, that makes sure it gets all the flags that are available. The problem is, of course, if you add a new flag later on, then the user application automatically gets that behavior as well, which probably it didn't want. So the implementation should always have this check saying, are the flags being specified that I don't know about? If so, give an error. Because then that allows user space to very nicely check on the kernel I'm running at in the moment. If I make the system call with this flag and I get an error back, then I know this kernel doesn't support that flag, this kernel version. The thing is, there's a surprising number of system calls that don't do it. Okay, those are just a few of them. Some of them are very old system calls. Some of them are more recent. You could add the check after the fact. So umount2 didn't have the check to start with, but it added it actually years later in 2.6.34. That's an ABI breakage. But it's probably safe to say that there are very few applications that use umount, and perhaps it was possible to find and fix them without too much pain. But it probably caused some pain. TimerFD, set time, added in 2.6.25, added the check 4 releases later. Yeah, okay, so I've already said that already. The problem is when you do that, you do potentially create an ABI breakage for user space. If you don't have this sort of check, then effectively user space ends up defining the kernel interface. Because if user space says, okay, I'm going to make a call with flags as -1, give me all the flags, then if later on we want to add a new flag to the kernel, you might end up breaking user space applications that do something strange. Okay, they do it strange, they did something stupid. But if we break enough user space applications that do stupid things, we simply can't make the change. You know, it's not enough to say to user space, oh, you've been stupid, now pay the price. Okay, and that's Linus's point. Okay, we don't even break user space applications that do stupid things. I suppose the corollary to that argument is because we allowed them to do stupid things in the beginning. There's other sorts of future-proofing failures that have happened in Linux as well. Okay, obviously 16 bits is going to be enough for user IDs, right? Okay, except by the time of 2.4 we realized it wasn't. Obviously 32 bits is enough for file offsets, right? Okay, it was 1991. Okay, you got a 100 megabyte disk drive in those days. No one was ever going to have a file as big as 2 gigabytes. Moore's Law, anyone? Okay, that was one I think we really should have seen coming. Okay, someone just decided, you know, let's just economize on a few bits here. Okay, the consequence of that is that nowadays, in crufty kernel space, we have old stat, stat, and stat64 that deal with these changes. And chown and chown32 and so on, and open 64 and so on. There's a whole pile of system calls in the kernel that were created to solve these problems when these kernel releases were made. The notion of maintainability of an interface can have some unexpected facets. So an example that I think is quite interesting is traditional Unix systems have this idea of root has all privileges. And applications are either unprivileged or they're root and they have all privileges. It's risky because it means that any time you want to give a user the permission to do one thing, if you make them root, you give them permission to do everything that root does. So it's a good gateway to security attacks on a system. So Linux added a solution which some other Unix-type operating systems also have, and also one or two other operating systems, called capabilities. Break the root privileges down into a number of discrete units. So for instance, if you wanted to change the owner of a file, then a process could just have the cap chown capability. Or if you wanted to send a signal to an arbitrary process, you could have the cap kill capability. Or capsysboot would allow you to reboot the system. So it's a nice idea, as at Linux 30, whoops, oh, hey, I'm slow. Linux 3.2 has 36 capabilities. Great. I'm a kernel developer. I just added a new interface. What do I use for my new feature? Which capability? Well, systems administrators do this sort of thing. So I think capsysadmin is the one I want. And this is the situation we have. Capsysadmin is the new root. 231 uses in Linux 3.2. I think there are something like 680 uses of capabilities across the kernel. 1/3 of them are capsysadmin. In other words, if you've written an application that requires, or a feature that requires capsysadmin, and that gets given to a user space process, we're back in exactly the situation we started with root. The game's over. I'll skip standards and portability. I'll just say that sometimes Linux has just violated portability for no good reason. And Unix, okay, this is Linux. I don't want to say it was just us. This historical problems too. Unix systems, even before us, messed this up. Okay, System 5's IPC, the API is awful. FCNTL locks, POSIX locks as they're sometimes called, have some really strange behavior with respect to closing of file descriptors, which means you can't use them in libraries. Select had a classic design mistake where its argument was, for the file descriptor sets to be monitored, was an in-out argument. You put it in, the kernel modified the same argument and sent it back to you. It meant you had to reinitialize it every time around the loop if you had a select inside a loop. So the number one classic mistake when you use select, I've got it in a loop, I've initialized it before the loop, and hey, it doesn't tell me about the file descriptors that are ready anymore, because I forgot to reinitialize each time around the loop. Overall grade that I give the kernel developers on interfaces, let's say it's a C+. It really could be a lot better. Can I take 5 more minutes, Marianne? Thank you. So why do these problems keep happening? I think there's 2 reasons that sort of go hand in hand. There's really an excessive focus on code as the object of value for a software project. And there's a poor feedback loop between the developers of a feature, or an interface in this case is what I'm interested in, and the users of that feature. So this brings me to my second myth, that code is always the best way to contribute to a software project or a free software project. There's that classic line, show me the code. It's a reasonable line sometimes. You know, someone says, give me this feature, or I think it's better done this way, it's a reasonable thing to say. Show me the code. But anyone can write code. And if the design is good, but the code is bad, the code can usually be fixed. And sometimes there are lines that I think are actually more useful in terms of a software project. They're going to give you more useful contributions, more valuable contributions than actually a code contribution. So just quickly, a few of those lines. Show me the user requirements. In other words, did you talk to a whole lot of users of this possible interface to find out what they might want? Is your interface going to be general enough to satisfy all of those needs? Is it going to be extensible for the future users who might want to use an interface in this space? Show me, this is a funny one for programmers, show me the design specification, the documentation. Well, if I don't have that, how do I know if the implementation deviates from the implementation? How shall I write tests? It turns out, and I know this from first-hand experience repeatedly, that writing documentation for an interface is a great sanity check for designing the interface. It also allows other people more easily to sanity check the interface. And I think usually, okay, I'm biased here, but a manual page is sufficient. It doesn't need to be some grand set of use cases, blah, 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 blah. Just a man page that clearly and completely defines or describes the interface. It is a question about when it's written, though, because if it's written after the interface is created, then typically it's too late, because you can't change the design. Show me the design review. That's a line you don't hear so often in kernel space. Did other people review your design? Did it fulfill those questions or those goals that I talked about earlier? Show me the tests. That's another line you don't hear quite so often. Did you write some tests? Did someone else write some tests? Because it's too easy to have tunnel vision if you're the creator of an API. Did you cover all the reasonable cases in your test? Did you cover the unreasonable cases? If you gave garbage input to this interface, did it deliver suitable errors back? When you wrote your tests, did you realize there were design problems in your APIs? What did you change in the design? What bugs did you find that you fixed? This is interesting information, okay, not just for you, but for the world at large, for other people who might create designs. So finally then, if you're a contributor to a software project, I think you shouldn't fall into the trap of thinking the best way I can contribute is code. I think there are other ways, and I've tried to indicate a few of those, and the reasons in those last few slides. And if you're a maintainer who's not encouraging those paths, those alternate paths of contribution, are you letting your project down? Thank you.
Някой, ако има въпроси? Въпроси?
So, Michael, how are you finding the reception for your book? Several months.
Let's say the community's been appreciative. Thank you. It has had nice reviews. Thank you.